So you are welcome, and I say good morning again. So the recording has started, and we will continue with lecture 6. Last class we discussed the binary logistic regression. I'm sure most of you may have had time to review that lecture. So another technique for classification, we talk about machine learning approaches. You have the regression approach and then the classification approach. So for classification or for regression, we've talked about the popular linear regression, the best subset regression. We have also used the penalized regression, the partial least square regression. So all of those techniques are meant for a situation where your output variable or the dependent variable is continuous, is measured on a continuous scale, where you have the output measure as discrete, then you will not be able to use them. So rather you use the techniques we started discussing last week, starting with situation where you just have two levels. So two categories, and you have to classify an object into any of these two categories. That's binary, dependent model. Now we look at another technique, even though it's applied to a discrete dependent model. That technique can be applied to situation where you have more than two levels. So where you have more than two categories. That's the beauty of the discriminant analysis. So we will, in the course of the lecture, we will take time to compare the logistics and the discriminant approach. So that's the rundown of what we want to discuss this month. So now I can, but before then, if there is any, before I start the lecture proper, if there is any quick comment, reactions, let me know. Is there anyone? None. So let's move on. Thanks to Honey for helping us to I'm sure you can see my screen.
Yes, sir.
Yes, sir.
Okay, so this is our classroom. You are already familiar. And I was thanking Honey for helping us to put the quiz on the platform. So you have the quiz on the discriminant analysis. I expect you to submit. You are expected to submit before 23rd. Ideally, it should have come. Your submission should be a pre-lecture quiz, but since it was uploaded very late, just yesterday, so that's why you have a double advantage of listening to the lecture and also reading before you make your submission. The other ones, I think a number of people have not turned in. Maybe only those who are committed to this course take time to turn in. So what I will do is to stop accepting responses from those who have not turned in. So we can do that so that we know those who are really committed to this lecture. So now to the subject matter. So the lecture note is here, lecture 6, discriminant analysis. So download and use it. Yeah. So the lecture or the material that you have, even though we can't cover everything in this lecture, so but you have the material, which you can always make reference to, not only for purpose of exam, even for practical application area. So I hope to see you employing these techniques in your research, your analysis, as much as possible. So I'm not sure how many of you are familiar with discriminant analysis. Maybe we start with that. Let me give you a quiz now, or a poll. Let's have a poll. I want to ask, have you used discriminant analysis before, or have you performed discriminant analysis before? Yes, no. I think it should be either yes or no. So, yes, you can respond to the quiz now. Have you performed discriminant analysis before? I got 2 responses, no, and the 2 said no. I still expect more people. Till we're about 10 in the class. So is it that you cannot locate the pool? I have 4 now. 1 yes, 3 no. Who is yes? Who is yes?
Hi, sir. I just saw.
Okay. So I'm coming back to you. Who else? I have only 4 votes. Um, I mean, Peter, you have to analyze voter apathy in this case. Now I have 5, 4 no, 1.
Okay, so Prof,
Yeah,
your screen is 1, so there are 8 more people. You are 1, I'm 1.
yeah, yeah.
So the apathy it doesn't exist here. They've all voted.
Okay, so no apathy. And now we
Yes.
have 6. So
Yes.
I think I get you right now. That's why I called the expert to help us. So, yeah, so only Ajasa. How I wish I'm Ajasa. So it's quite very skilled, heavily to know. So that's interesting. Ajasa, you want to share your experience before we continue on discriminant analysis? What did you use it for?
Though I've not used it before, but I did it on the corner level under multivariate analysis. So we did discriminant analysis. We used to classify data sets. That's what we use it for. We used to classify data set. That's to some like two classifications. That's the essence of discriminant analysis based on the particular criteria. So that's what we use for that time. Though I've not used it myself, but that's what we did it on in corner level under multivariate analysis.
Okay, I was thinking maybe you have done a consultancy project or any um, any job that require that you use it, or either.
Yeah, I've not done it before. I think I've done it now. I've gotten more knowledge about it.
Okay, so so let's continue that. But thank you for that information. So discriminant analysis and our discussion. I mean, at the end of this lecture, our if you are able to thoroughly go through this lecture material, the key objectives are: 1, you should understand the principles and the mathematical foundations of discriminant analysis. What's the principle and what is the mathematical foundation? We are not going too deep into the mathematical foundations, but just a little guide will be provided here. Then we will soon know about the two approaches, the two major techniques in the discriminant analysis. That is the linear and the quadratic. So we will differentiate between the two. So at the end of the lecture, you should be able to also distinguish between the two, and most importantly, know when to apply each of them. You will learn about the assumptions that underlie discriminant analysis. It's a multivariate technique, and most multivariate techniques, they have distributional assumptions and other pertinent assumptions. So you will also know the underlying assumption for discriminant analysis and how do you validate those assumptions, whether the whether the exist or not. Then one key objective of this lecture is for you to have the ability to apply this technique to real-world data set and perform classification problem. Classification problem is most frequent, this thing. And I've given you several examples. When you are doing admission exercise, for instance, a news applicant is coming. Should I admit this student or should I not admit? That's a classification problem. You are in the bank, you want to decide whether loan should be given to a loan applicant or not to be given. That's a classification problem. So you have most issues in life that are that bordered on the classification problems. So in this lecture, you are going to, I expect, hopefully, that you know how to apply this technique to classify objects or individuals. Then you will also be able to evaluate the performance of your discriminant analysis models. What are the performance evaluation techniques that you can employ to be able to say this analysis or this classification is good or not? So these are the key topics, introduction, and so on and so forth. So let's just go to introduction to discriminant analysis. First, we need to know that this technique is used in machine learning, just as, in fact, most of the techniques in machine learning, econometrics, and so on, they are statistical techniques. So it's also used in machine learning, purposely to predict categories, to predict whether an individual or an object will belong to a particular group or not. You cannot, for instance, see a student and say this student is a cultist or not. So you may use this classification technique to, if you have data about students, cultist and non-cultist students, you can discriminate. In fact, the word discriminate is simply mean to separate, to say this is this, this is that, is to assign to appropriate group or class. So it's used in machine learning, and as I said, you can have different classes. So, but there are all assumptions. The assumptions, as we'll see later, makes it different from the logistics, because logistics assume a logistic distribution, a logistic distribution. So this discriminant assumes a Gaussian distribution. So that's very important that we know. So when we talk about the types, but before I leave, the main purpose of discriminant analysis, you have to get that right, is simply to predict a categorical dependent variable. That is the main thing. So you have a dependent variable And I think I explained that last week. So you have your dependent variable and you have your independent. So this is appropriate only. Remember, your dependent variable can be continuous, can be discrete. And for discrete, of course, you can have two categories or two classes, and then you can have three or more classes. So we discussed logistic last time. Logistic can be used here, no problem. You know, particularly we say binary logistics. So we say binary logistics. But for this, we can also use discriminant that we want to talk about. And then we can also use it, in both two classes and situation where you have three or more classes. We will talk about the independent variable. You recall that in the case of logistics, your independent variable could be continuous, could be discrete, could be discrete, could be ants, etc. Could be anything. But it's not like that in the case of discriminant analysis. It only requires that for discriminant analysis, your independent or your regressors or the features as used in machine learning. So it could be independent, could be regressors, and so on. But in machine learning, usually you use features. So for discriminant analysis, the features are usually continuous. So because it requires that they follow a normal distribution, and any variable that will follow normal distribution will have to be measured or on a continuous scale. I hope I'm communicating.
Yes, sir.
Good.
Yes, sir.
So what is the purpose of discriminant analysis? Simply to predict a categorical dependent variable. So, and how does it do that? By analyzing the linear combination of the predictor variables. I've explained to you. So the dependent variable could be x1, x2, x3, x4, and so on like that. And then the usual style is to look at the linear combinations of this, and I can call it. So if there are two groups, maybe group Z1, then I would need to form the linear combination of this group, which will be, I can call it A1 X1 plus A2 X2 plus A3 X3, and so on like that. So this is the linear combination for the group Z1. For the group Z2, I can have B1 X1 plus B2 X2 plus B3 X3. This is the linear. So since my dependent variable has two groups, Z1, Z2, then I have the linear combination for each of the groups. So this is how discriminant analysis, this is how it works. So the linear combinations of the predictor variables are then analyzed, to be able to predict the class or the categorical, the class or the category, as the case may be. So now we can talk of types of discriminant analysis. We have the linear, we have the quadratic. So we use the acronym LDA for linear, QDA for quadratic. So the assumption in the LDA is that I just explained that we have two groups. So we have two groups which so you have one class, this is another class. Maybe this class, these are those who vote. So you may want to predict whether somebody will vote or not. So this class, those who did not vote. So you are predicting based on age, based on income. You are predicting based on years, age, income. Let's just use that too. There could be other variables as the basis. So these are the predictors. These are the predictors. So you will be predicting whether a voter will, an eligible voter will vote. So you are predicting class 1 based on age and income. And you are predicting class 2 based also on age and income. So we want to make distinction between LDA and, of course, the QDA approach. So the LDA approach assumes that the different classes, the C1 and the C2, the data for the age of C1, the data for the class of C2, they are based on different Gaussian distributions. So that this is still Gaussian, the data for this group is based on Gaussian distribution, but the Gaussian distribution is different from this Gaussian distribution. So they are based on different Gaussian distribution. But even though they have different Gaussian distributions, they have the same covariance matrix. So if Z1 is the first one, so maybe it has a multivariate normal distribution, with a mean, and then a covariance matrix. So this one will have different mean, so its own mean will be this, but Z2, the second class, is also multivariate normal with mu, but its own mu will be different. But the assumption is that the two of them have the same covariance matrix. That is the LDA. That is the LDA. So the LDA assumes that each class has its own Gaussian distribution, right? But they have the same covariance matrix. So this is the covariance matrix. So, however, the quadratic discriminant analysis, because this assumption is very, very, very strong, very difficult to to achieve. So the QDA relaxes the assumption of equal covariance matrices across the classes. So it allows for each class. So in QA, each class has its own. So in QDA, so Z1 is multivariate normal. So it has its own mean vector. So with its own covariance. Z2 has its own multivariate normal with its own main vector to its own covariance. That's what makes it quadratic. So this allows for the separation of classes with a quadratic decision surface. That is, if you go to the theory, I know if you go deep to the theory, you talk of the quadratic decision surface and so on like that. So this is the difference between QDA and LDA. This is the difference. Is it clear to everybody? We are now 13 in the class.
Yes, sir.
Okay. What is clear? Tell me what is clear.
That the assumption for using the LDA
Yes.
is when the they have different distribution. That is the mean, but their covariance is the same. Why the other one QDA?
You need to learn how to use the terminologies appropriately. A Gaussian is a normal distribution. Is that okay?
Distribution.
And a
Okay,
normal
sir.
distribution is characterized by
Mean
two
and
parameters, the
parameters
mean.
and variance.
Because this is multivariate, so it has a mean vector, and
Yes, sir.
then have the variance covariance.
Covariance matrix.
In the univariate, that's when we are testing hypothesis, you say that the variances are equal or the
Yes, sir.
variances are not equal.
And not equal.
So in this case, yeah, so let me allow you now to learn just to.
Okay, sir. At least the category that we have C1 and C2.
Yes.
So they are distributed normally Gaussian, that's normally distributed with the same mean, different mean, but the same covariance matrix.
Excellent.
But in under QDA, so I
Yeah,
said under LDA, since that
yeah,
assumption is not that easy to achieve,
yeah,
then QDA try to relax the assumption,
yeah.
whereby they have a different normal, they are distributed normal with different distributions of mean and covariance matrix.
Okay. Now, why do you think I want somebody who is a bit intelligent? Everybody is intelligent. I even have very cerebral, people. Yeah, everybody here is intelligent. But let's do a bit of discussion around that concept. And I've used this example. Suppose you have a group of eligible voters, and it's now time for them to vote. You want to classify whether one will vote or the other will not vote. Let's look at the category of those that vote. Let's look at the category of those that will not vote. Do we believe, why do we, what do we expect the variability to be? Do we expect the variability among those who vote to be the same as those who don't vote, even though they are eligible? Do you understand my question? Does anybody understand that question?
The variability is based on what?
Okay, you have in this group, let's even say in this class, we have the rich, we have the poor. Dr. Afolabi is among the, where do I classify you?
Which?
The rich, the rich, the rich, the rich, sir, the rich, sir,
Okay.
the rich, sir, the rich.
Okay.
Masses, among the masses.
To be a doctor is not easy. The rich.
I'm also among the masses. But let's do the classification the other way. Let's say in this class we have those who are being sponsored, and those who are not being sponsored. Those who are being sponsored, those who are not being sponsored, who sponsor themselves. These are two distinct groups. So anybody in this class will know the class he or she belongs. Am I correct? Femi, which one do you belong to?
The sponsored, sir.
The sponsored. Hamid, yes? You are still thinking.
Sponsored.
Self-sponsored.
Yes, sir.
Okay. Dr. Olowokere now.
Self-sponsored.
Self-sponsored.
It's proud that sponsored you.
So we have distinct groups now. Excellent. My concern now is that if I collect data of age, of income of those that are being sponsored and those that are self-sponsored, do I expect the variation in these two groups to be the same?
No, sir.
Why?
In our own case, no, sir.
Huh?
In our own case, no, sir.
What do you expect? What do you expect?
They are not going to be the same.
What do you
They are
expect?
not going to be the same.
Okay,
They are not going to be the same.
Do we
Yes,
all
sir.
agree? Do we all agree?
Prof,
Yes.
can I attempt something, sir?
You can attempt. Don't
Yes.
even attempt. You are supposed to even establish something.
So, Prof, I'm going back to that voting example.
Okay. You like that?
Yes, I want to use evidence-based research to answer, so that I think it will help us.
Okay.
So, when you look at the class of people who vote most of the time,
yes,
and you compare the features,
yeah,
you will see that the variability is minimal because they have the same persuasions. But when you now look at the second category, there are many reasons why people will not vote. So bringing that to what Amit is trying to say, the variability will be there. And I think that's why QDA is a solution to LDA's weakness.
Excellent. That is the point I want to make clear, that you should know the distinction between these two approaches, because the underlying assumptions for them differ. So why the LDA assumes that the variabilities among the groups are the same, among the various classes they are the same, which sounds a bit no, not so logical, not so realistic when it comes to application. And I've given you quite a number of examples to show that it's not good, it's not likely to be in that. Yes. Yes, Badmos.
Okay, so thank you, Prof. Thank you, sir. Sir, can we look into these cases as an example for the case of developed country and developing country?
Mm-hmm.
Because if we check very well, for those developed countries, we check them, their variability is not that much. They almost
Wait,
have the same thing.
Badmos, don't speak out of context. What's your classification problem? That's the starting
Okay,
point. What are you
okay,
classifying?
okay. I want to classify the countries that are developed and the ones that are not developed.
And do
Developing
you
and
need
developed country.
uh
Badmos first. No, no, no. Those are the
it's
classes.
it's
Those are
like
the
you want
classes.
to classify whether somebody is a man or is a woman, or you want to classify whether
Those are the classes.
you know there are natural classifications.
Okay, sir.
You don't need to, there is no model that will predict whether you should classify me or I should classify you as a female or as I should classify you. That's a natural classification. We will still come to situations like that because in the animal kingdom you have species, but it's always difficult to separate those species. So what to do often is you use another technique, but the kind of thing we are doing now is not for natural classification, except if I'm also and you should know when to, I mean, you don't need a model to say, to predict if somebody is a female or a male. You don't need a model to predict whether a country is in Africa or is in Europe. You don't need you don't need to you don't need a model to predict whether UI is Federal University or is or is you don't need that because those are I hope that helps you. If you have a clear problem that you want to solve that will require that you classify countries, it's possible that you want
Yes,
to
sir.
classify countries into yes.
Yeah, you can use the example that we have started before to compare. Maybe
Okay.
he has not understood it. That's why the one of that among us that you use, sponsors are not sponsors, so that they were able
Okay.
to understand it.
Oh. Bad
Okay.
boss.
Thank you, sir. I got you, sir.
Does it make sense to you now?
Yeah, we can proceed, sir. I'm
Okay.
checking whether like we can get some countries that are developed and the ones that are not developed. So all those things like that.
No,
No
is
problem, sir.
Nigeria developed? Badness. Is
Ah.
Nigeria developed? You are laughing. You are
No,
laughing.
no,
I
Eh?
mean, I mean, Badmos,
Yes, sir.
what Prof is saying is before you can use classification methodology, you must
Okay.
have a problem that you are trying to tackle. In your own case, you are only going to work on an existing classification. There are already developed countries and underdeveloped countries. So if there is something that you are looking at, maybe inflation or poverty, and then you now begin to talk about their responses, then you have a research question. All right.
Thank you, sir. Thank you, sir.
Yeah.
Thank you, sir.
Okay. Because except if a new country will emerge tomorrow, and then you now want to discriminate which class with this new country. Should we classify this new? But there are even, so should we classify this new country as developed, not developed? Then we can look at the features of the, so as of today, there's no classification problem as far as this thing, because no new country, we are not going to classify a new country. No new country will emerge. Classification problem is used when you will have a new, new observation, that you now want to classify to say, okay, this new one will be in this, and then you'll be able to measure whether your classification is true or not, whether you have classified correctly or you have classified wrongly. But all countries have been classified as at tomorrow. There can be countries that will move up later and so on. Yeah, fine. But no new country is going to come up except Nigeria is finally allowed to go. Even at that, you cannot, any country coming out of Nigeria cannot be classified as developed, because the country is emerging from a developing country. So it cannot be, if 100 countries emerge from Nigeria, all of them will still be developing. Okay, so time is really flying fast, but wherever I stop, that's where you will read the rest of the lecture. So, but I want the foundation to be well laid so that you can get the remaining. Okay, I'm going to, so let's look at the mathematical concepts. So the idea is there must be a separation criteria. So, which means you have something like a plane, you have something like a plane where the objects are, and then you are able to, you have a criteria that will allow you to say, okay, this is Z1, this is Z2. So there will be a criteria, the basis to assign one to one class and to the other. You remember in the logistic regression, the moment you compute the probability, you compute the logit, which gives you probability value. So if that probability is equal or greater than 0.5, then you classify into a success group, and otherwise you classify into the failure group. So that is a criteria for classification. The same way in the discriminant analysis, we call it the separation criteria. So you determine a line, a plane, or a hyperplane that will separate the observations into groups based on their on their uh, on their predictors. So you will use the age, in the case of voter, uh, you know, voting, those who voted and those who did not vote. You will use the age, the income as the basis to classify. Then another concept that is very important is the dimensionality reduction, uh, which is very prominent in the linear discriminant analysis, because we've talked about high dimensionality data. That's when you have too many variables. If you have too many variables, then there is a possibility of multicollinearity. And then it becomes very difficult to really separate groups. So when you have high multicollinearity, which is likely in the situation of high dimensionality, when you have too many variables, then you will need to do dimensionality reduction. And this is usually done using the principal component analysis, which we are also going to look at in the course of this lecture. So those two concepts are very important: separation criteria and dimensionality reduction. Let me quickly edit something I found here. Okay. Okay. So what are the applications? Discriminant analysis is widely used across different fields in finance, credit scoring models. You use that to predict if a borrower will default or not. In marketing, you want to predict whether a customer will buy a product or will not buy a product. You want to predict whether a customer will shun or will not shun. Whether a customer will move to another competitor or will not. You want to predict whether the it's about classifying your customer, into segments, into groups, based on their purchasing patterns. In medicine, you can also use discriminant analysis to classify patient outcomes, whether patient will respond to treatment or will not respond to treatment, or whether patient will recover or will not recover, whether patient has a disease or does not have a particular disease. So you can use classification. There are some diseases where it's difficult to really, even though the symptoms, because there are some diseases, they have similar symptoms. It's always very difficult to say, okay, this is actually the disease. So it's difficult. So this model can be used to classify patients. Again, in admission, in academic, in education, it's difficult for me to know those who will graduate, those who will not graduate. the performance will, but the model can predict even before graduation. Even at the point of admission, the model can predict whether it's also used to discriminate is a student called a cultist or not. So you can do a discriminant analysis can work very well. Can you also suggest again, these days you have issue of biometrics. You know, pictures are now being analyzed, images analyzed, even finger, prints being analyzed, or facial features being analyzed. So in today, you can use discriminant analysis also to recognize an individual based on those characteristics, to classify them based on those characteristics. So by facial look, you can be able to say this one is is a criminal or is not a criminal, is of certain origin. Who is talking?
I said also to classify plants into species.
Exactly. So you can use that to classify plants into into species. That's good. So, what are the advantages? Won't waste time on that. You can read that: efficiency, performance, interpretability. So read that. But let's quickly look at the mathematical foundation of the LDA. So for the linear discriminant analysis, as earlier said, mentioned, it assumes that the different classes, the different groups, they are generated under the same Gaussian distribution, but with different means, but with the same covariance matrix. I've explained that very carefully. So let's assume we have those classes, C1, C2, those are the classes. And that tells you that you can have more than two groups, more than two classes, but they will all have common predictors, X1, X2, X3. So the assumption is that the classes have their own means, but they have common variance. And with the common variance is what we now call the pooled covariance matrix, which is denoted as the SP. So the discriminant function for the linear is given by that expression. Y is equals to that WT. That's the transpose of that expression plus B. That W is defined as the pool variance, and that is given in the first bullet there. So that pool variance is what is considered to be what connects them together. So B is the constant derived from the prior probabilities of the classes. So that's just a brief explanation of the discriminant function. So the most important is that expression, which will help you to classify the individuals into their respective classes. The fundamental assumptions, one is that those predictors, X1, X2 to X whatever, they are normally distributed, which means the predictors, the features, can you have a dummy variable there? Can you have discrete variable there? Can
Under the
somebody
pictures, no, sir.
know why?
No, sir.
Why?
Because based on the assumption that
So,
it has to be continuous.
so it has to be continuous. That is one major thing you have to know. Each predictor, in fact, in normal linear regression, we don't worry too much about the distribution of the predictor variables. In even in logistics, we don't worry about the distribution of the predictor variables. The predictor variables of the features can come from any distribution. We don't worry too much about the underlying distribution. But for the discriminant analysis, we must ensure that the predictor variables they are normally distributed. Then, two, it assumes homogeneity of variance covariance. We've talked about that the variances across the groups or classes, they are the same. Independence of observations is also another critical assumption, that the samples are drawn independently. In other words, the samples are random. They are random. So randomness is very important in it. Randomness in statistics guarantees independence. And we must always ensure that our observations are random, except, of course, in time series observations are sequential, they cannot be random. So, in most classification, most cross-sectional, analysis is randomness is very, very important. So, what are the steps? What are the step-by-step process for performing the LDA? The starting point, you compute the mean of the vectors. In other words, you get the mean of each class. So you get the mean of each class. And then you compute the pool variance, this pool variance, SP inverse, you get that. And then you compute the linear discriminant expression that you have here, this expression, you compute it, and then you project the data onto the either line or hyperplane to be able to get the coefficients. And then you now classify observation by assessing their coordinates in the new space defined by the linear discrete. So based on the line that you have created or the hyperplane that you have created, you can now classify the objects. We will do that in our examples. So we have example here which you will also reproduce on your own. So this example that I've used comes from, the data comes from mass package. Mass package is a package that you can, it comes with R. So I use it. I got the, so yes. So I got the package from, you can go to packages and then you can look for mass package. So if you don't have it, then this is mass package, which means support functions and data set for variables and replace mass. So this package, if you don't have, just go to install and type mass. So you will see it double S. So you will see, it comes, actually, I think it comes with the R base. So you can download and install. So if you install, you will see the functions. You will see the functions. So there is a data set there in that package, which has is on I'm coming. That data is called iris data. It's a popular data set, and it contains measurement of 150 iris flowers from 3 different species, making it a very good example. So you have 150 iris flowers, and measurements were taken on each of them, and then you now classify them into their different classes. So what are the measurements? The length, the width. So we have the sepal length, the sepal width, the petal length, and the petal width. So those are the measurements taken from each of them. And they are classified, there are 3 groups. You have the group called Setosa group, versicolor group. I think the 3rd group has virginica group. So there are 3 species. So if you run, so this is the first 6. This is the first 6 observations in the data. This is the sepal length, one of the features. This is the sepal width, the second feature, sepal length, that's another feature, and then the 4th feature is the petal width, and then the species, Setosa, this for the first 6. This is the summary of the data. So you have the minimum, the first quarter, the median, the mean. Remember, as I said, it is assumed that each of these predictors, they follow normal distribution. Very important. So it's possible to get the minimum, maximum, first quartile, median, the mean, and so on. So that's the descriptive statistics. The dependent variable here are Setosa. Those are the classes, versicolor and virginica. These are the classes, and there are 50-50 observations in each of them. So I provided a sort of explanation on those descriptive statistics. So you can go through minimum, first quartile, the interpretation of all these results. You can see them there. Then we now perform the LDA, that's the linear discriminant analysis. There is this function in the mass package which will enable you to perform this. So there is that function. That function is LDA. So if you go to, this is the function which helps you to perform linear discriminant analysis. take your time to learn about this function. So this is the function, and in the function, you have arguments. So you first of all put the formula. The formula will have dependent and so on. In our case, species is our dependent variable, then followed by the data. There are other arguments which you may put or not, but the basic argument will be the formula and the data. So that's why here you have, this is the formula, which is indicating your species as the dependent, then the tilde sign, which is like your equals to, then the dot here simply means all the predictor variables in the data set should be used. So, and we have 4 of them: sepal length, sepal width, sepal length, petal length, and petal width. So that's what that dot. If you are not using all of them, you can list them and use plus to connect them. Then the second argument, which is very important, is the data. So you need to indicate the data. In our case, the data is iris. Then you have the results. In the result, that gives you the probability of any flower being identified as Setosa species, or being identified as versicolor species, or being identified as Virginica species. So they all have equal probability of being, because there are 50-50 of them. So that is the probability, the likelihood of any flower being assigned to these groups. And these are the group means. The group means for sepal length, you have the means for each group, for sepal width, for petal length, and so on like that. And then this is coefficient of the discriminant function for LD1 and for LD2. This is the proportion of trace. All these results are also explained here. The group means, the coefficient of the linear discriminants, the proportion of trace, which indicates the proportion of the total variance explained by each. I need to also make a correction here. Sorry for that. I hope the class is following me.
Yes, sir. I'm following you, sir.
Yes, sir.
Yeah, so you need, if you have questions, just answer. Let me quickly correct few things to make it. Okay, so you have the prior probabilities, that is these prior probabilities, which I've explained. So the group means, these are the group means. So you have that. Oh, still not what I want. Still not what I want. Mhm. Okay, now this is what I want. So these are the means of each predictor variables that what you see here. These are the group means for each predictor variable. So Setosa has the smallest, if you look at the group means, you know, Setosa has the smallest mean in that group, and you can also follow the discussion on the rest. Then the coefficient of discriminant of the linear discriminant, that's what you have here. So these are the coefficient for LD1, coefficient for LD2. And the proportion of trace, which indicates the proportion of the total variance explained by each discriminant, that's what you have here. So you see that LD1 has the highest proportion, 0.9912. LD2 has the very, you could only explain 0.88%. LD1 explain 99. So this means that LD1 is very effective for discriminating between the species. So that will be used. So you can see the remaining interpretation. So here, the petal measurement, when you look at the length and the width, they are very effective in distinguishing between the species. I leave take time to study the output and the interpretation very well. But finally, you can see the plot. So the command or the function that you use to get the plot is what you have here. So the model is this is the LDA model that you have fitted. So that is what is called out here in the plot function. So you use the plot function, the dimension, and then the color you want to choose based on the iris type. The legends, this should be on the top right. That's why you have the legend on the top right here. And then the levels, 3 levels of the species, and then the field for each of the 3. So you can see these ones, they are the Setosas, they are completely distinct. They are completely distinct, well separated. But you can see sort of a good part of vas color is well separated, and a good part of Virginica is also well separated, but there are conflicting areas, they run into one another. So you may not have a perfect separation. So this is the so you can now make prediction based on this, and you use the predict function to do that, and it will predict the classes. So these are the predicted species for these classes. And then you can now use confusion matrix to now know those that are correctly predicted and those that are wrongly predicted. As a matter of fact, the Setosas were well predicted. No zero cases of predicted, no case of Setosa is wrongly predicted as versicolor, and no case of Setosa is wrongly predicted as Virginica. But for versicolor, we have two cases of versicolor that were predicted as virginica. So this is a wrong prediction. We also have one case of virginica wrongly predicted as versicolor. So this is also wrong, but you can see the accuracy altogether. The accuracy is the sum of these 50, 48, 49 divided by 150. That's the total. That's what gives us this. And that's what this expression tries to calculate. That's what it tries to calculate. So that is the way to run the analysis, to run the LDA. Is there any question on that?
No, no question, sir. Understood.
No. So then the quadratic, the QDA, of course, you already know now that each of them is assumed to have its own covariance. So in terms of the difference between LDA and QDA, one, you can look at it from the assumptions. The LDA assumes that classes have the same covariance matrix. I've explained that. QDA does not assume that. So each class has its own variance covariance. Then in terms of complexity, the LDA is simpler and it tends to be more robust, particularly if you have smaller sample sizes or when the assumption of equal covariances truly holds. Then LDA is simpler, it's easier. But QDA provides more flexibility because it relaxes that assumption which is difficult in practice. So it allows you to work with individual covariances instead of pooling covariances. But that's additional cost. Additional cost of computing the individual covariances. Then, in terms of decision boundary, LDA we produce a linear decision boundary, which is considered to be more efficient. But QDA is going to use a quadratic decision boundary. That's the difference. So that's why it's even called the quadratic discriminant analysis. The linear one is what I've explained before. The quadratic is what is provided here. This is the quadratic expression for discriminating. Whereas for the linear, it's only taking the linear combination. This is the discriminant function. For the quadratic, this is the expression. And it's quadratic because of this. So you will have this thing for each K. Each K represents the class, the number of groups that you have. Remember, you have C1, C2, CK groups, and you have this number of predictors. So you also will have K variance covariances. So each of them will have their own expression because there is no pooled listing. So that is the mathematical difference between the two. And then well, we still use the same data set, to the iris data set, to demonstrate the quadratic. And then one issue that came up in my analysis, okay, let's continue. One major issue that will likely occur is the problem of multicollinearity, because if that happens, that can really cause what we call rank deficiency in group. Rank deficiency. And when I ran it, it couldn't run because of that problem of multicollinearity. So, and you could have rank deficiency when fitting the QDA model. You know, it's usually a serious problem, and it could arise because of collinearity. It could arise because of small sample size for the predictors. It could arise because of perfect, because of perfect separation. The perfect separation is the example I gave before. Gender is perfectly separated, male, female. So it's a perfect separation. And if you are bringing that into if it's a predictor, if it's one predictor in your model, that could lead to, if you put gender, for instance, which will perfectly separate any individual, that can lead to problem of rank deficiency in your analysis. So it happened in this iris data, and then I now needed to check what the problem was. So that led to checking for collinearity. So the first thing I did was check for the collinearity and looking at the correlation matrix. So this is the correlation matrix. So again, I use the variance inflation factor to now check whether there is the severity of the collinearity. And then so for each group, this is what I have for sepal length and so on like that. So this correlation matrix and the variance inflator factors, these are also explained, the correlations are explained here. The result of the variance inflation factor, they are also explained here. And then so the conclusion actually is that if you look at the variance inflation values, 3.42, 1.31, 3.89, we expect that the values should be greater or at least greater than 5 or 10. This is usually a rule of thumb, not fixed. Some will use 5, some will use 10 as a threshold to indicate severity of the multicollinearity. So, but in this case, if the FIF values, even though they are a bit higher for sepal length and petal weight, but they have not exceeded 5. They have not, or not to even talk of 10. So, but it still suggests some degree of multicollinearity, only that is not severe. So we could suspect problem with strong correlation, with petal length, better weight in our data. But for SEPA weight, the correlation is, the FIF is quite low. So it doesn't have a strong multicollinearity with other predictors. So you could look at these interpretations, and therefore, since we suspect issues, then we might need to go the route of dimensionality reduction. So that is done using the principal component analysis, and this is how the PC is run. So, and then this is the result of the important components, PC1, PC2. So this is the standard deviation. This is the proportion of variance. If you are not familiar with principal component analysis, you just have to start looking at it. So here we now extract the first two principal components for PC1, because if you look at the proportion, this one is able to explain 72%. This one is able to explain 22%. So PC1 and PC2 generally seem to explain a very large percentage of the variance. So, we extract the two principal components, PC1 and PC2, and then combine them with the data so that we have a new variable. So this is the internal structure, the data frame now, because the PC1 has been extracted and added to the data set. Then the predicted species have also been added. This is the actual species. This is the predicted species. This is the PC1 extraction. This is the PC2 extraction have been added to the data frame. Now, having added that, we can now run the QDA to be able to overcome the problem that we saw. Instead of now putting the four predictors, we are now putting the principal component as the predictor. Sorry, the extracted PC1 and PC2 as the predictors, not the original variable any longer. And that gives us this result. And the interpretations, they are also provided here. So you also have the summary of all these results here. Take time to go through them. There are other things that could be done. You could add regularization, which I try to do. You could also, if the problem persists for QDA, then you can resort back to FDA. So that's what I try to do here. And then here we have the final output. So the probabilities still remain after we have run the QDA. This is the formula. Remember, we are now using the extracted principal component, component 1 and component 2. And then this is the group means for PC1, PC2. And that allows us now to be able to classify. And after the classification, let me just go straight. After the classification, which you see here, this is the result that we have. So for the actual, these are the labels. For the predicted, these also are the labels for Setosa, for Versicolor, for Virginia. So this is the the rundown of the application of both the LD and the QDA. Well, in the remaining time, which I didn't do, you will have to do the model evaluation and selection. So first of all, you need to evaluate, always bear in mind the need to evaluate your model. Evaluate the predictive. We also evaluated this, I think we did, looking at the accuracy for the QDA was 0.92. You see, QDA is much lower in accuracy compared with the LDA. So if you look at the LDA accuracy that we got the other time, do you still remember which was yeah, so that 0.98 accuracy, which means 98% of the flowers were correctly classified, which is quite so if you are to choose between QDA and LDA, which one will you choose now? Of course, you will choose the LDA because of its predictive power. So sometimes this is how you choose, you evaluate your model. So it will not have made sense for you to just go and use LDA and go like that. It's always good to evaluate by comparing alternative models. So choosing between, we've discussed this before, choosing between LDA and QDA, you need to consider the assumptions. We've talked about that. You need to consider the complexity and the size of your data. If you have good data, you have large data set, that will be QDA will be a very good one. If you have a more complex, more data points, more, you have high dimensional data set, QDA will be preferred. But if you have very few observations and so on, LDA will be preferred. Then predictive performance, QDA provides a significantly better predictive performance than LDA, provided those conditions are satisfied. But in our situation here, we have not done cross-validation. So if you have sufficient data points, you can do cross-validation to be able to see. But experience has shown that QDA sometimes we outperform the LDA. If your interest is in the predictive performance, even though the one we did now, LDA outperforms the QDA, but we have not done cross-validation. So we have not trained the data, we have not tested the model in a new data set. That's what cross-validation will do. If your interest is in computational efficiency, then LDA is considered to be more computationally efficient than the QDA due to its very simple structure. You have only one discriminant function to deal with. So methods of assessing the accuracy of discriminant analysis model, we have used confusion matrix to look at how many were correctly and wrongly classified. So, and then so there are other measures from that confusion matrix: the accuracy, precision, recall, F1 score. Try to know about those ones. They are all explained here. I think I've also given you this before. Yes. So the receiver operating characteristics, ROC, and the area under the curve, they are also used, they are graphical methods anyway, plots that can help you to evaluate the accuracy of your discriminant analysis model. If you are to do validation, then you need to do cross-validation, or you use the bootstrap methods. We have not used those. In cross-validation, you split your data. There are several cross-validation techniques: k-fold, two-fold, and so on like that, sequential, different cross-validation techniques can be employed. You can also bootstrap. So here you have, even though I didn't run it, but in mass, you can fit the model with this expression. You can do cross-validation with this function, with this command. You can also get the confusion matrix and the ROC curve with this syntax. And then you can print your results with this print command. I didn't do that. You might also need to do it on your own. There are assumptions and diagnoses. We've talked a lot about those assumptions: normality, homoscedasticity, for particularly LDA, which assumes that the variances are the same; the independence, randomness that I've talked about; absence of outliers, very critical. These assumptions, you have to check them. You can check them. So here I've given you details how you can check for normality. You can use graphical methods by plotting the histogram, or by plotting the QQ plot, quantile plot. That can give you information about skewness and kurtosis. You can use statistical tests, perform Shapiro-Wilk test, Kolmogorov Smirnov test to check for normality. There are over 100 tests of normality. So then you can also perform homoscedasticity tests to see if the groups are having the same variances, whether the covariance matrices are the same. You can use, because this is multivariate, you can use the boxes M test. And this is only applicable if you are running the LDA. So normally before you run the LDA, it's good that, before you run the linear discriminant analysis, it's good that you run this test to be sure that truly the covariances are the same. You can also use the Leibniz test, as an alternative for checking for homoscedasticity. How do you check for independence? It's more about the design of your study, how you collected the data. You must be able to convince your reader or your audience that you have not introduced any hidden bias into your data collection process. You can check for outliers using distance measures like Mahalanobis distance. You can also visualize to see if there are, use box plots, which will give you upper quartile, lower quartile, middle quartile. It will easily show you if there are outliers. You can also use a scatter plot to inspect. So before you run discriminant analysis, these are the assumptions that you have to check. How do you handle violations? If you have non-normality, then you can transform. Transformation is one way. Log, square root, inverse transformation can help you. If you have non-parametric, you can also use non-parametric methods for your approach. Heteroscedasticity, you can, if you have heteroscedasticity, then it means for LDA, there is a violation. So you simply switch to QDA. That's what that's the option you have. So once the assumption of homoscedasticity fails, then you shift to QDA straight away. You can also use the regularization techniques. So you switch to QDA once there is heteroscedasticity. Once you have outliers, there are several approaches to deal with outliers. One of them is to remove the outlier if you can justify the removal. If you know that it is truly illegitimate, that could be a way. There could also be other robust methods that are not so sensitive, not so sensitive to outliers. You can also use those techniques. After you have been able to address the violations and you now run the model, then you can diagnose the model, look at the residuals, look at the classification error rates as we have done, look at the model comparison, compare the models in different way. So you can use this syntax to be able to perform all the things, check for outliers, plot residual, check for normality, and then use the box M plots. These are, so to check for boxes M test for homoscedasticity, you have to upload or install this biostat 3 package. Before we close, I think we are almost done. We are not going to waste time on this. These are advanced topics in discriminant analysis, just to call your attention to them. Not that we will dwell on them. So now we can talk about regularized discriminant analysis, kernel-based discriminant analysis. For those who want to settle in this area, then we talk about dimensionality reduction using the LDA, yes. So these are benefits of that. Then in terms of the applications of discriminant analysis, I've mentioned them earlier, but in more detail, you can apply discriminant analysis to finance problem if you are dealing with credit risk assessment. I look forward to people who will do projects, and I've been sharing a lot of conferences with you. whether in energy, in economics, and so on. You can apply these techniques, submit. And now, if you are doing masters, you are probably looking forward to do PhD, and you want to be a researcher. So there are so many problems that you can apply these tools to, that you can showcase. So credit risk assessment in finance is one. You can write a paper, you can submit, attend, participate in conferences and present your work in this area. Marketing, customer segmentation, biometrics, facial recognition. I think you are also doing a course on image recognition. Am I correct?
I think we did that last.
Pattern recognition.
Pattern recognition, not image recognition, right?
Yes, pattern recognition.
Okay, whether pattern recognition or not, you can also apply this discriminant analysis. I think that's the end of the lecture. These are practical challenges you may want to discuss among: dimensionality, assumption, scalability, and so on. I have practical questions and suggested solutions to you. You can look at those questions, and then finally you have the multiple choice questions which have been uploaded. We have 4 minutes to, yes, I know this note is quite extensive, about 33 or so pages, but I told you I have my own objective. That's why sometimes it takes time to work on the lecture note. So it's important for you to devote quality time to review the material. They are not meant for the exam purpose alone. They are also meant for your future use. I hope later to publish these things in a book that you will be able to possibly add to your library. Thank you very much. Are there questions? Questions? Comments? The class is too quiet. Some people have even left. Let me, Dr. Olokere, thank you very much for yesterday.
Thank you very much, sir. Hope it went well, sir. I listened to it.
It was this morning I listened to it and I enjoy it. Maybe, please help me to appreciate the Peace. And I think her name is Peace. So I'll come and appreciate that. But we might need her more. I'm not even sure if we will not need her next week or whether.
I have a couple of them, so we can interchange and we can talk on this.
Okay.
Anytime you are not available, just tell me or tell her to get something to focus.
Wow, thank you. How I wish I have people in this class who can also be able to do these things.
Some of them are here. Ajasa, you can. Badmos and Joseph. Let them they can talk.
We can put them on the hot seat. We put them on the hot seat, and if they do blunder, they will also come back and get the feedback.
Yes, they can do it. Send me almost all of them. Boko Bong, all of them, they are.
But they run away when you want them to. You won't see
there's always a first time.
They always hide. If not for Peter and Hodney, but this time around, we will deliberately set you up on a steep mountain and then ask the trailer to run behind you. So I think that's the only time for you to learn and also perform. So on this note, I want to say thank you. Any question, takeaway question? If not, enjoy your weekend. Hamid, you want to say something?
No, I'm not asking question. I just want to say thank you, sir. That really appreciate, sir.
You are welcome. You are welcome. So enjoy your weekend and of course take care of yourself. Bye.
Thank you
Thanks,
very
sir.
much.
Bye.
Thank you very much, sir. Thank you, sir.
Thank you, sir. Bye.